All right, here's chapter 5, probability distributions. First, again, we'll just kind of review and preview what we're going to do. We'll do random variables in 5.2. We'll talk about binomial probability distributions in 5.3. 5.4, we'll do mean, variance, and standard deviation for the binomial distribution. And 5.5, we'll talk about the Poisson probability distribution. So kind of a review of what we've done before and where it's going to take us in the future. So chapters 2 and 3, we basically learned how to collect sample data, make graphics, and generate summary statistics from it, right? Such as the sample mean, the sample standard deviation. Chapter 4, we started talking about the probability of outcomes and events. And what we're going to do is tie both those together in chapter 5. It makes basically making a theoretical model that hopefully describes that experiment that we might have done and describes the behaviors that we should expect to see in our experiment. And then we get what we call parameters. So we have our sample statistics, and these are going to be our parameter, like basically our population, what we would generate from our theoretical model of what would happen in the long run. So some of the key concepts here is we're going to introduce probability distributions and how they work. We'll introduce random variables associated with those. We'll also talk more about the unusual events, in the sense that they are unusual and that they don't occur by chance, or they are not likely to occur by chance. And we'll introduce, like I said, random variables. We'll distinguish between random variables for discrete variables and continuous variables. And you might recall discrete is finite and countable. Continuous is infinite and countable. Not countable. Infinite many variables. So we'll develop formulas for finding the mean, variance, standard deviation for a probability distribution. Determine whether outcomes are likely to occur by chance or they are unusual, right? So in the sense that they are not likely to occur by chance. So 5.2 is random variables. Random variable is a variable typically represented by x. So if you look over here on the right table, we have x is the number of p's with green pods. So 0, 1, 2, 3, 4, 5. And so you could tell that this is the discrete probability distribution because these are discrete numbers, countable and finite. This is our random variable, x. This is the probability that corresponds to that random variable. So in other words, the number of p's with green pods for the problem, like 2, if x equals 2, like 2 p's with green pods would be about an 8.8% chance, or 0.088, and so on. One thing you might notice about our probabilities, they all lie between 0 and 1. If you sum these together, what do you get? Yes, 1 is correct. You're going to find that basically probability distributions must have that the summation of all of the p of x, or basically the probabilities corresponding to the random variables, must sum to 1. So this is a probability distribution over here, if you haven't figured that out. But yes, it is. So we have two things: discrete random variables, which is what that example was last time, right, just on the last slide, and then continuous random variables. So in discrete, it's finite number of values or countable number of values, or countable refers to the fact there might be infinitely many values, but they can be associated with a counting process. So the number of values is 0, or 1, or 2, or 3, etc. Examples could be like hens laying eggs, the number of students in the class, the number of M&Ms in a bag of M&Ms candy. Continuous random variables have infinitely many values, and those values can be associated with measurements on a continuous scale without gaps or interruptions. So an example could be the amount of milk produced, the amperage in your car battery, the amount of rain or snow received on a given day. So are the following discrete or continuous random variables: the weight of gold Knox stored in Fort Knox, the number of people who own cars in Wyoming, the number of Twizzlers you eat in a day. Yes, so hopefully you figured out that the weight of gold stored in Fort Knox is continuous random variable. Remember, it's like a weight, right? But let's suppose I asked you the number of gold bars, like individual bars stored there, then it'd be discrete. But in this case, since you're talking about weight, you should think continuous. The number of people who own cars in Wyoming, that would be discrete, yes. And the number of Twizzlers you eat in a day would be discrete. But if I said the amount of poundage of Twizzlers you eat in a day, which sounds hilarious, would be continuous, okay? So think whole numbers, usually going to be discrete random variable. Think where you could have fractional units. You can think weight, basically on an infinite scale or continuous scale. So probability histograms. So every probability distribution must satisfy each of the following two requirements. Notice that there are 3 below. That's because some textbooks have just the 2 and some have the 3. I put that in there so you guys make note of it. First one is there is a numerical random variable x, and its values are associated with corresponding probabilities. When it says random variable x, that's these variables here. Notice that these are numerical. It's not things like yes, no, I don't know. These are like 0, 1, 2, 3. They're numerical. We can perform computations on them. Therefore, they are numerical. You'll see why that's important when we go and talk about how we can calculate the mean, the variance from probability distribution. 2, we have the summation of p of x is equal to 1. Right? That means the sum of all of these equals 1. Note, right, if you sum some of these tables, they might be equal to 0.999 or 1.01 or 1.001. This can just be because of rounding errors, okay? So don't get too worked up if it's like 0.998 or something like that. All the probabilities lie between 0 and 1 inclusively. That means they could be 0 or they could be 1. So here is a probability histogram. So basically you took, whoops, let's go previous. I accidentally double clicked there. If you went to the previous slide before this, you'd see 0, 1, 2, 3, 4, you see the probabilities. Now, if we interpret those with a histogram, you can see whether it's normally distributed or if it's skewed or whatever it might be. Point being, this is another way of interpreting basically those probabilities. So you see that basically 4 pods is probably the highest and 3. So if we're going to calculate the mean from the probability distribution, we'd see it's probably going to be around in here somewhere between 3 and 4. Yeah. Now, normally we do this in class. We construct one of cars people own and stuff like that, but we can't because we're online here right now with this video. So let me ask you this question. Does the following satisfy probability distribution? So if we go back, is it numerical? Yes, 0, 1, 2, and 3. So checking the requirements, that's the first one. Next one is, does this sum to 1? I don't think it sums to 1. It doesn't. So therefore, this would not be a probability distribution. Right? If you sum these probabilities together, if it doesn't equal 1, then it's not 1. Yeah, so that's this one. Doesn't satisfy number 2. Does the table on the right describe probability distribution? Hopefully you heard my foreshadowing. I said yes, no, I don't know is not numerical. So this does not satisfy the first criteria. So therefore, this table would not be. Here's another one. Does p of x equal x over 10? So this is basically, you can also write probability distributions or probability distributions in a functional notation. So this is saying basically for each random variable, suppose it's 0, 0 would go here, x equals 0, so 0 would be up here, so the probability of getting 0 is 0. And then 1, so the probability x equals 1 would be 1/10, right? Put the 1 in there, 1/10, and then we'd say x equals 2, 2/10, 3, x equals 3, so 3/10. Yes, if you sum those together, it equals 1. So yes, it would be a probability distribution. So when to discuss salary, senior executives, when asked job, applicants should discuss salary, and the table is based on their responses, based on the data from account temp survey. Does the table describe a probability distribution? So numerical, yep. Sum these together, no. That's only 0.7, only 0.66. So it is not a probability distribution. Now, the reason why I would keep going over some questions that may seem easy about whether this is a probability distribution is we need to know this first before we can perform any of these kind of calculations like the mean, the variance, and the standard deviation. So these are the formulas that we'll be using, and you'll want to probably have these down in your notes. Mean for probability distribution, mu, is going to be equal to the summation of x times p of x. So what happens here is you take the random variable and you times it by its probability, and then you sum all of those ones together, and that's how you get the mean. Down here, you take the random variable's value minus the mean, square it, and then times it by its probability, and you do that for each term. That is the variance. And obviously, if you take the standard deviation, you just take the square root of it. This is probably the easier one for computations, and I'll show you on the next slide how we can do one for data set. So here's one for the p-pod. We'll calculate it for this. So we want to calculate the mean and the variance. So on this next slide, here is how we calculate the mean. So x times p of x. So you take the random variable's value times its probability, you get a number, and then you sum them together. And in this case, we get 3.752. That is the mean from the probability distribution. So remember how I said it probably lies between 3 and 4? That's where the mean is, 3.752. Now, this other one, this is the harder to calculate formula, but maybe easier to understand. I have another video that I've done one of these. If you want to just watch that kind of video, you should be able to find that as well. X minus mu squared times p of x. So we take the x value minus the mean, we square it, then we times it by its probability. We do that for all the calculations, and then we sum it together, and then that gives us our variance. Rationale for the formula is 5 through 11 through 5 through 4. Here's basically how it works. So I'm going to calculate the mean for the summation of the frequency times the random variable divided by the population. So if you think about it, frequency and the total population, if you added all the frequencies together, you get basically capital N. Capital N over N is 1. And so hopefully you'd see that this is just basically a fractional unit of the random variable. In other words, a percentage. And that's how you get that F over N. So in other words, if you had 10 out of 100, that would result in 1/10. And that would be your probability of X occurring, of that event, if you counted that up. It's kind of neat. The round off rule is kind of nice. I know some of you guys might have questions about how many decimal places should I carry. One more decimal place than what the number of the original data set had. Usually do your rounding at the very end. Don't round prematurely. Okay, we won't calculate it for our class because we can't do that one. Identify the unusual results with the range rule of thumb, the maximum usual value, and the minimum usual value. And these should look kind of familiar. You might have seen these before when we did x bar plus 2 times the sample standard deviation, for when we wanted to figure out max and min usual values for things we did in the past. Now we're translating them for basically doing them for a probability distribution. Basically, we can find that mean from the probability distribution, and we can find its standard deviation, and we can find its max usual value and its minimum usual value. So again, rare event rule, right? If under a given assumption, such as the assumption that a coin is fair, the probability of a particular observed event, such as 992 heads and 1,000 casas, is extremely small, we conclude that assumption is probably not correct. In other words, the assumption that the coin is fair. It's probably not fair. Yeah. Again, just a reminder, unusually high number of successes, right? If the probability of success is really, really small on the chance of just by chance, then you'd probably say there is some influence happening in there. And vice versa when you want to think of unusually low. So asking you guys this question, does the given information describe a probability distribution? So we have job interviews based on information MRI networks. Some job applicants are required to have several interviews before a decision is made. The number of required interviews are corresponding. So one interview corresponds to 9% probability. 2 interviews, 0.31 probability. So does the information describe probability distribution? So we got to check the assumptions. Are the random variables numerical? Yes. 1 interview, 2 interview, 3 interview, 4 interview. Yep, they're numerical. Do all the probability values sum to 1? Yes. I think this case that is summed to 0.999, but very close to 1, so we'd say yes. Do they all lie between 0 and 1 inclusively? Yeah, they all do. All right, so assuming that the probability distribution is described, find its mean and standard deviation. So its mean, if you want to pause and try to calculate it on your own, is 2.85, and its standard deviation is going to be 1.23. Now, that is the standard deviation. The variance, though, is 1.5075 if you calculate it out, just so you know. So using the range rule of thumb to identify the range of values for usual numbers of interviews, is it unusual to have a decision after just 1 interview? So in this case, we would say no, it is not unusual, because we find that our minimum usual value is 0.39, And our max usual value is 5.31. So it would be unusual to have 6 interviews though, which would kind of make sense. It seems kind of rare to have that many. So expected value, the expected value of a discrete random variable is denoted by E, and it represents the mean value of outcomes. It is obtained by finding the value of the summation of X times P of X. More formally, E is equal to the summation of X times P of X. So you can think of basically the expected value equal to that. Note it, an expected value need not be a whole number, even if the different possible values of X be all whole numbers. Let's do an example here. So here's the expected value for life insurance. And this is how, for example, they calculate insurance policies. So actuaries use this in actuarial science. So in this example, we have a 0.9986 probability that a random selected 30-year-old male lives through the year, based on data from the US Department of Health and Human Services. A Fidelity Life Insurance Company charges $161 for ensuring that the male will live through the year. If the male does not survive the year, the policy pays out $100,000 as a death benefit. From the perspective of the 30-year-old male, what are the values corresponding to 2 events of surviving the year and not surviving? Well, if you survive the year, you're out $161. If you don't survive the year, well, you're still out the $161 because you bought the insurance, but you also now get $100,000. So you get the difference between those two. In theory, you'd be like, well, I'm dead, so it doesn't. But again, from the perspective of them, not necessarily what happens when they're gone. B, if a 30-year-old male purchases a policy, what is the expected value? So in other words, is it in his best interest to buy this? Like in the long run, what do we expect? And then finally, can the insurance company expect to make a profit from many such policies? Well, you'd hope that they could, but here's how we do the math, right? The probability of lives is 0.9986. Probability of death would be 1 minus lives, right? I said lives, lives. And the values associated with each are negative $161, and $99,839. You might be wondering, how did you get that? That's the 100,000 minus this 161, and that's if he lives, okay? Or if he dies. If he dies, either way, he is out the $161, but whoever his beneficiaries, they'll get that $99,839 or amount. Actually, they'll get 100,000, but his expected value. If a 30-year-old male purchases the policy, what is his expected value? So his expected value is going to be the random variable times the probability of that random variable, and then the random variable times the probability of that random variable. So he's going to be out $21 in the long run if he does this policy. Can the insurance company make a profit? Yeah. Yes, the expected value for the insurance company is $21, which indicates that the company can expect to make an average of $21 for each such policy. So kind of a recap, combine methods of descriptive statistics with probability. We talked about random variables and probability distributions, which led to probability histograms. And from there, we did the requirements for probability distributions. We also talked about how to calculate the mean, variance, and standard deviation of a probability distribution and identifying unusual values. And finally, briefly, the expected value. And that is all of 5.2.